from Austin in Poland, who's going to talk on homotopy nilpotency of Moore spaces. Please.
Okay, so thank you very much. So good morning, first of all, to everybody. So it's really my great pleasure to attend CRM workshop on homotopy theory and group theory. I would like to express my deep gratitude to all organizers, especially to Harris Brotto, thanks to who I start from him my discussion about possible participants, and I was in touch with Joachim and others. So this is my great thanks. I'm really grateful to organizers for inviting me here. Okay, so the title of my talk is on homotopy nilpotency of Moore spaces. The nilpotency is notion from the group theory and is known to everybody, I think. But I'm going to say something about extension of this notion on spaces, especially on Moore spaces. An abstract of my talk is, let MAN be Moore space of type AN, where A is a billion group and N is at least 2. I'm going to say later something more precisely on Moore spaces, but let me mention that Moore space is somehow a generalization of sphere. If A is the infinite cyclic group, then it's exactly sphere. And we show that Moore space is homotopically potent if only if A is a subgroup of additive group of rational numbers. Okay, so this notion of Moore spaces is really known for n greater 2, but also we can say something about Moore spaces of type MA1. And so at the end of my talk, I'm going to discuss also nilpotency of such kind of Moore spaces. So if A is infinite cyclic group, then MA is of course a cycle. Okay, so before we start the main result, we need some preliminaries. So all spaces and maps we assume to be connected based with homotopy type of CW complex, unless we assume otherwise. And we write the classical notation. So if you have a pointed space, then omega x, respectively sigma x, is the loop space or suspension of x. And also if you have two spaces, pointer spaces, xy, then xy in the square bracket with the node set of homotopy classes of maps from x to y. Okay, so if you have a space, then identity with the node by iota x, and then given a space, we use the well-known notation, namely we consider the wedge of spaces and smash product. Smash product is the quotient of product of the exactly square of Cartesian square of x by wedge, and it is called smash product. And then in topology, there is a notion which is generalization of the notion of the group. Namely, the notion is called H space. H comes from Hopf. The space is called Hopf space or H space if it is a pair exactly, where X is a topological space and mu is a map from Cartesian square of X to X, such that this diagram you see on the screen is commutative but up to homotopy. That is exactly the meaning that the mu has identity up to homotopy. An H space is called group-like space if X satisfies all axiom of groups up to homotopy. It means that it's associative and there is a notion of inverse. There is some known result that if you have H space with CW and it's homotopy associative, then always has homotopy inverse. So from now on, we assume that H spaces for us are group-like. Okay. And now, given an H space, we can factor we can consider a unique contract factor where x is fixed, and then we could evaluate for any space. So if x is H space, exactly if it's group-like, then this factor takes value in category of groups. So one may ask when those factor takes their values in various subgroups of groups. For example, if x is homotopic commutative, that is, then this is if only if this factor takes value in category of abelian groups. Okay, but now we are going to discuss something about nilpotency on the level of H spaces. So first recall that if you have any abstract group, then this group is called nilpotent if it has a lower center series, and such that elements of this sequence are given like this. So gi plus 1 is defined by gi, that is simply commutator. That is the definition by induction. And we say that this group is nilpotent if this is this sequence terminating in the trivial subgroup after finitely many steps. The smallest n, such that the G has a central series, length of n is called nilpotency class of G, and is denoted in literature by nil G. And this notion we can extend on H spaces. Namely, given an H space, we consider sequence of maps. So we start from identity, that is phi1, and phi2 is exactly basic commutator. Because our space is group-like, then we can consider notion of basic commutator. And then we consider iteration of this. So we define by induction phi n plus 1 as composition of this basic commutator, and then compose with phi n across identity for n greater or equal to. And now we can define the nilpotency class of H space. So it is by definition, it's the least integer n for which this map phi x n plus 1 is homotopy trivial. And we call it homotopy associative H space, homotopy nilpotent if it happens. If not, then we simply say that the nilpotency of such H space is infinite. Not like for groups. Also, this definition could be formalized in other language, namely, if you consider smash power of any H space, then we define another sequence of maps, namely, if for phi bar 1 we put a phi 1, and then we observe that you have map phi n, then this map factorize through smash power, and this map which we get by factorization will denote phi bar. And we have following fact. Let x be any n space. Then phi xn is homotopy trivial if only if phi bar with the index is homotopy trivial. Though we have another equivalent definition of nilpotency. Also, we have definition which comes from Bernstein-Gannea result, namely nilpotency of any H space could be described as follows. First, that is superior of all nilpotency classes of homotopic classes of Cartesian power of X to itself. And that is the same as nilpotency of homotopic classes of and smash product of X to X. And finally, that is the same if you take superior of nilpotency classes of map from Y to X, where Y is any topological point space. Also, there is a result by Zabrodsky, which states that a connected H space is homotopy nilpotent if only if this contravariate factor determined by a homotopic hom of the category of all spaces is nilpotent group values. Though this generalization what we observe for homotopic commutative groups. Although it is equal, we need following observation. If X is H space, if H subspace of H space, and there is a map R from X to X prime with this H rectrax, then we can easily derive that nilpotency class of this subspace is less equal than nilpotency class of space from which we start. And this notion, which first was introduced for H spaces, could be extended on any topological space. Namely, it is well known that if you have any space, then if you consider loop space on this, then loop space is group-like H space. So we have this observation, then given any base space, we associate with this space integer with this nilpotency of loops on X. And this number we call nilpotency class of space. And first we have very simple observation that nilpotency class of pi1x is less equal than nilpotency class of loop space. From this it follows that if you have space which first homology vanish, so if first and space is connected, then if first homology vanish, it means that pi1, that this abilization of pi1 vanish. So that is the case if pi1 is perfect group. So if space is has a perfect first homotopic group, then it follows that the nilpotency class of this space is infinite, because perfect group is not nilpotent. But such spaces exist. For instance, if you take space which has homology isomorphic to sphere, and this space is not one connected, then fundamental that pi1 of such space is perfect. And now we give an extension of this result, I mean this inequality, involving Whitehead product. Okay, so if you have two elements from homotopic groups of space, then we consider Whitehead product alpha 1 alpha x, which belongs to homotopic group with the appropriate index. And then next we define n+1 fold Whitehead product, which is denoted by alpha 1 alpha n+1 in square brackets, and this is exactly some simplification of what was written there. And we have, okay, and then if you iterate this Whitehead product, then we have notion which is called W length. W comes from Whitehead, namely the W length of X, or is called Whitehead length of the space, is the least integer n, such that the iterated Whitehead product alpha 1 alpha n+1 is 0 for all alpha from homotopic groups of space X. If no such integers, then we put that Whitehead length of space is infinite. And again, we recall some nice result by Bernstein and Galea, which says that Whitehead length of X is the lower bound for nilpotency of loop space on X. So many results on homotopy nilpotency have been obtained, but homotopy nilpotency class has been determined in very few cases. So let's start from well-known space, namely Thomson sphere. It's well known that if you take loop space on M sphere, then nilpotency of loop space on the sphere is 1, if only if M is equal to 137. That is consequence on this result that only H space on sphere exists for S1, S3, and S7. That is this well-known result by Adams. Okay, and then we have following result that if you consider Whitehead length of sphere a nilpotency class of omega sphere, then those two numbers coincide. And this number is equal to 3 if n is even and not equal to. If is equal to if n is odd but not equal to 137 and n is equal to 2. N is 1 if n is 137. Those are the cases where you have this H structure on a sphere. Okay, so for spheres we have no secrets. Everything is known, and Whitehead length and nilpotency class of loop on sphere coincide. But if you have sphere, then you can consider wedge of spheres. And then we can see that nilpotency class of omega on the wedge of spheres is infinite. This is written that is consequent on theorem 1.5, because 5.5 says that Whitehead length is its lower bound for nilpotency. So we have to show that Whitehead length of a wedge product of spheres is infinite. But it's true if you look on the Hilton theorem, which describe homotopy group of wedge of spheres by means of spheres from which is start. So you can see, if you look on the proof, that the iterated product doesn't vanish for any length. Also, we have other spaces about which we know some information about their homotopy nilpotent. Namely, consider projective space over reals, complex number, and quaternions. Then the homotopy nilpotency of loop spaces of projective space has been first studied by Jana and Stein, and then their p-localization by Meyer. And Jana and Stein show that homotopy nilpotency of loop on the real space is finite if a dimension of this projective space is odd, but it is even, then is infinite. Also, it was shown that, but for complex numbers, studies show that nilpotency class of projective space is not greater than 7. But recently, in one of my papers, it was shown that if you have a projective space over quaternions, then this nilpotency class is finite, but unfortunately is unknown up to now to me. Maybe there is some literature. What is the value of nilpotency class of projective space of complex of quaternions? But anyway, we know the result that this is finite. Also, generalization of spheres, Stiffer manifold, generalization of projective space like Grassmannian. Also, you can show, using the same method as for a projective space over quaternions, that nilpotency class of Grassmannia and Seifert manifold over complex numbers and quaternions are finite. But over reals, it is not in general, but their p-localization have been also you can evaluate are finite. Okay, so now we move to Moore spaces, from which we begin our talk. So let's say some details. So given an abelian group and n integer n greater 1, a space X satisfying this property that homotopic group of this space are 0 if I is less n, and homotopic group of X coincide with group A, and higher homology group of X are trivial. Such space is called Moore space of type AN, and is denoted by MNN. As a CWC complex Moore space with n greater equal to exists, and its construction is given as follows. So first, we construct the space for free abelian group. So if F is a group, F is a free abelian group, and its n is greater or equal to, then Moore space of such group is defined as the wedge of sphere, and the number of spheres is equal to set of free generators. Also, you can show, using this construction, that you have homomorphism of free groups. Then this homomorphism could be extended to a map of Moore spaces, which we construct in part 1. And this map has this property. So if you apply homology factor, then the homology of this map is equal to homomorphism from which we start. And thanks to this construction for free spaces, we can now construct Moore space for any group. So now, given an abelian group, we consider free resolution. Okay, so if you have group A, then for a abelian group A, then there exists not necessarily unique a free group which cover this group. So we have epimorphism, and subgroup of abelian group of free group is free. So we have resolution where F1, F0 are free groups. So now, if you have this is map from F1 to F0, then taking the construction from the second part, we have a stellar map F from Moore space on F1 to Moore space of F0, and such that value of homology on this map is equal to map phi from this resolution. And next, we consider push-out. Push-out, namely, we have the map F, and this vertical map is simply inclusion of Moore space to a cone on this Moore space, and then we consider push-out, and push-out of this square is a space for which we are looking on, and that is Moore space. And we can show also that this Moore space is uniquely determined by A. That is somehow it is not difficult to show this, but I don't want to go to details. And from uniqueness, it follows that every Moore space, if n is at least 3, is a suspension of the previous Moore space. But also could be shown that Moore space of type A2 is also suspension of some CW complex. This CW complex, which is denoted by LA, is not unique, but exists. So anyway, we have information we are going to use later on that Moore space of type MAN, if n is at least 2, exists, is unique, and of this space is suspension of subspace, of some other space. Also, we can say something about Moore spaces of type A1. That's the result by Varjari. And if you show that Moore space of type A1 exists, okay, so first there is definition. So MA space is an MA space is only if its second homology. Okay, so sorry, that is not definition. It is definition, we know what it is. Okay, the various result is that MA space exists if only if second homology of this group A over integers is 0. This property for the second homology group of A is 0 could be expressed in another rule. There is a rule by Miller that second homology group of A, if A is abelian, is 0 if and only if the square tensor product of A coincide with some group generated by diagonal. I mean, generated by squares, tensor squares of A. There also a result where second by Miller, which characterizes in similar way, but is much more complicated, where second homology of any group varies. No, but for a abelian group, we have simplification of this result. But homotopy type of Moore spaces is not uniquely determined by A. There is a result constructed by Hatcher, and it is constructed like this, that you take smash of cycle n Sn and glue somehow n+1 cell. Then we have inclusion of res1 and XX, and this inclusion induce isomorphism or homology group. And on the homotopy group by K is not less. It is less equal n. K is less n, but it is not isomorphism on pi n. So we have two Moore spaces of type Z1, which are homology spheres, but not have not the same homotopy type. So also the case M1 is quite delicate, not for any space, or this space exists not for any group. Also, is not uniqueness, but for any if n is greater than 2, then we have uniqueness up to homotopy. Okay, so now we first concentrate on Moore spaces of type AN. So, is to formulate some result, which I'm going to use later, we need some notation and recall some definition. So given a space, we write I1, I2 for the canonical inclusion of X to the Cartesian product. And also we have diagonal map. And so now if we have a homology group of A with coefficient in A, where is a group, then we say that element of this homology group is primitive if the value of induces map on homology by diagonal on this element is equal sum of values of this element alpha on the induced map on homology by the canonical inclusion of I1 of I2. Okay, so using this notation, we have it's a following result. Those now consider reduced homology of X with coefficients with the field. And the proposition is, if the reduced homology of X with coefficient in the system field F has at least 2 primitive generators, where F is field, then then it means that suspension and loops and suspension of X is not homotopy nilpotent. So I have no prepared proof, but there is some idea. For the proof, we take homology of X with F coefficient and make use of the both Samuelson theorem. Then we get that homology of loop of X of suspension of X is isomorphic to tensor algebra on the reduced homology. This also can be written in another way, ULL, where L on the reduced homology is the free Lie algebra generated like this, and UL is a universal enveloping algebra. Next, we consider iterated Samuelson product from from smash power of X to loop on suspension of X. And this product we define like this. S1 is simply the canonical map from X to loop on X. This comes from adjointness of omega and sigma. And then we iterate this by Samuelson product. So if X1, Xn are from reduced homology, are primitive, then tensor product of those elements belongs to, of course, to n power, tensor power of homology, but it's the same as homology of the case smash product of X. And is sent by induced map by SK to iterated bracks. It is the sense of Lie algebra. In particular, if X and Y from the reduced homology are distinct primitive generated, then the class that defined by using the structure is in the unit. Hence, we can say that that SK cannot be null homotopic. And that is the key observation, which we are going to apply now to consider homotopic nilpotency of Moore space. Now, to conclude the proof, we have that this is map SK from the smash product power of X to loops on suspension. There is factorization, and this one of the map of this factorization is exactly the map which we consider, that is phi bar, we consider to define homotopic nilpotency of H space. So because SK is not homotopic trivial, we have that phi bar is not null homotopic, provided this SK is so. But we have this from algebraic result. And now we are going to use this result to state something about homotopic nilpotency of Moore space. So first, we concentrate on Moore space, which is determined by cyclic group of order being some power of prime number. So we have Moore space of type ZPMN, where P is some prime number. So if you consider now reduced homology of these Moore spaces and take coefficients with a simple field Fp, then we have that for k equal 2, that homology is isomorphic to Fp. If k is equal n plus 1, then it's isomorphic to Tor ZPM Fp, but it's isomorphic to Fp, and is 0 otherwise. But we know that Moore space, because we assume that n is at least 2, is suspension of suspension of the previous space. So now we consider the iterated Samuelson product, which we have used in the previous proposition. No, but this homology has two primitive elements. So from this, we deduce that nilpotency class of such Moore spaces is infinite. Sorry, here is something is wrong. Sorry, what happened? Okay, this is so homotopy nilpotency of loops on such Moore spaces is infinite, but n is at least 2. Okay, but for us it's also interesting the case where m is infinite. Namely, we are going now to discuss the nilpotency of Moore spaces where we have ZPM that is a preferred group. But for preferred group, we have a problem. Namely, tensor product of preferred group and ZP is 0. The reason is that ZP infinity, its preferred group, is divisible. So if you consider tensor product with this with FP, it is 0. So reduced homology of Moore space determined by preferred group with coefficients at P is only concentrate in dimension Kn plus 1. This group is towards ZP infinity FP, but it is isomorphic to FP. So the argument used in the previous corollary collapse because we don't have two primitive generators. But this problem could be overcome. And to do this, we consider some mapping telescope, and then we apply corollary 2, and also use, so corollary 2 is about ZPN, where n is finite. Also, we can use, using this trip by mapping telescope, the nilpotent class of Moore spaces determined by preferred group, ZP infinity, is also infinite. But why we start from this? Okay, so consider the following cases. Now let A be a abelian group with element of finite order. That means that any element in this group is torsion. Then is well known from the group theory, is not triggered a result by Kulikov, which say that A contains a direct summand, ZP, for some P, and M could be not only any number, but also infinite. For instance, the group ZP infinite, it doesn't contain direct summand ZPN. Nobody, so Kulikov results say that such group, that any abelian group has direct summand. But if you have this, then it means that if you have any abelian group, then this abelian group is isomorphic to the direct sum of ZPM and some other abelian group. M could be infinite. No, but Moore space has this property that if you have direct sum of groups, then Moore space on the direct sum is the wedge of the factors. So if A is isomorphic to direct sum of ZPM B, then Moore space on AN is just a wedge of Moore space of ZPN and N, and this Moore space on the B. But we have shown that Moore's homotopy nilpotency of Moore space ZPN is infinite. And from this construction, you see that Moore space ZPN is the retract of this space. So if you have this, then we use the remark which we mentioned at the beginning. We deduce that nilpotency of Moore space with A is, if A is a torsion group, is infinite because nilpotency of ZPN. And that was the reason why we start to analyze nilpotency of Moore spaces determined by cyclic group ZPM when M it is from 1 to infinity. Okay, so we have that if A is abelian, sorry, and torsion then nilpotency class of omega of Moore space is infinite. Okay, but now consider other equation. So now given a group, if you consider the tensor product of this group by rational numbers, then you have direct sum of some copies of Q. And that the number of the direct of the summand is called a rank of group. The rank of group could be defined as dimension of the vector space over Q of tensor product of A and Q. Then for reduced homology of this Moore this space, in this case, the Moore space determined by the tensor product of A and Q are concentrate only in dimension n, and is exactly direct sum of some copies of Q, where the number of copies is equal to rank, and 0 otherwise. Okay, and next, given nilpotent space X and a set of primes, we consider localization of this space with the for if a localization. Then by Mayer result, we have if X is nilpotent space, then, and suppose that nilpotency of omega X is less n, then nilpotent localization is also less equal n. So from this it follows that if nilpotency, by contradiction, that if nilpotency of localization is infinite, then nilpotency of omega X from which we start is infinite. And in this one, we're going to use the Pleiser. But Moore space, if n is greater to 2, is suspension. Then again, we can apply this construction using this Samuelson product. So we have a map from smash power of Moore space of type A with tensor Q n minus 1 to loop space on suspension. So if now suppose that the rank of A is greater to, then by the previous proposition, we have that nilpotency of Moore space determined by AQ is infinite. Then from the proposition by Mayer, we deduce that nilpotency of Moore spaces from which we start is infinite. So if rank of this group is at least 2, then it's also infinite. So now, the last case, third, we have to concentrate on a abelian group where a rank of A is 1. If rank of is torsion free, because if it has a torsion, then we have the result by Kulikov from which we deduce that nilpotency class of such Moore spaces is infinite. But this well-known result that if group is torsion free and rank 1, then this group is subgroup of additive group of rational numbers. Also, we have to here some result that if you consider Moore spaces of type Qn, that's the same as the localization was here, and it's the same as Eilenstein space if n is odd, because the other homotopy group are only concentrated in one dimension. Therefore, we have that MQN is homotopy commutative in ACT, and nilpotency of MQN is equal 1. Okay, now, but let's come back. That is some remark, but let's come back to our group A, which is subgroup of Q. Any group, subgroup of Q, if it has this property that is a direct sum of the infinite cyclic group. The reason is that a group of rational numbers is locally cyclic. It means that any finitely generated subgroup of rationals is cyclic. So any group is colimit of finitely generated subgroup, but finitely generated group is cyclic for Q. So we have a sequence of cyclic group, and such that A is colimit of this sequence. And now, if we have this sequence, then with this sequence we can associate construction which is called in topology mapping telescope. And this telescope, it leads to a sequence of spheres. And now using homotopy nilpotency of loop on sphere, we deduce that nilpotency class of omega on some Moore space of AN, where A is subgroup, is not a torsion-free subgroup, and it is subgroup of Q, is not greater than 3. So we have only one case where nilpotency of this group, a Moore group, is finite, and to be true, the Moore space is really close to the sphere. If A is Z, then it's exactly sphere. Okay, and finally, we can state the main result. If you have Moore space, if N is at least 2, then nilpotency class of loops on Moore space is finite, if only if A is torsion-free with rank not greater 1. Or A equivalently, A is subgroup of Q. Using this result, we can easily to get the following conclusion. Suppose we have sequence, M is greater 1, and we have sequence of positive integer N1 and N. And we have also sequence of Moore spaces, M, A, K, and K, of type AKN if K is from K equal 1. Then you can show that the nilpotency class of omega on the product of Moore spaces is finite if only if AK a torsion-free group with rank not greater 1. And that is a conclusion, a simple conclusion from theorem, the previous theorem. Namely, if you have omega of the product, then omega, the loop, then the loop commutes with the product. And then if you look on the definition, or also as a result by Ganea, you see that the nilpotency class of product is the same as maximum or nilpotency class of a factor. But also we have some result or nilpotency class of a wedge of Moore spaces and of course a loop of wedge spaces. We claim that a nilpotency class of this space is finite if only if M is 1 and this group for A1 is torsion-free with rank in this 1. And this is consequence of this result that nilpotency class of retract is less equal to nilpotency class of space, which we start, and also of course this we can also use the main result about nilpotency class of Moore spaces. So I think I have only 8 minutes. That's right. So at the end, we can say something about Moore spaces of L1. So we have a construction by Hatcher of space of type Z1, which is not a sphere, but we can show that okay, so we need some preparation. So pi one of this the space is strictly group, and then also the generator by T. And of course, pi one acts on higher homotopy group, and you can show using this this construction that n homotopy group of X is integer which is extended by 1/2. And this action is given in such a way that the action of T on alpha, where alpha is element of this pi n, is multiplication by 1/2. And consequently from this, we have that you consider weighted product T alpha, then is minus 1/2 alpha, and then if you reiterate, then you have the iterated weighted product of n plus 1/4 is equal minus 1 to n alpha. So it's not real. So, but weighted product is the lower band of the nilpotency class of the loop on the space. So from this result, we deduce that the nilpotency class of such Moore spaces, of which is constructed by Hatcher, is infinite. Now we consider another example, which is generalization of real projective plane. If n is equal to 2, then of course we have real projective space. So this, so we glue cell of dimension 2 to S1 using a map from S1 to S1 of order n. And that is the Moore space of type Zn. Where Zn is a cyclic group of order n. And then you can show that homotopy group of this space is cyclic group of order n, and that's TB generator. And next, we consider second homotopy group, and this you can show that the second homotopy group could be identified with the group ring of Z over Zn. And that's right. It is generated by alpha equal to 1 on T. Then still we can also consider, like in the previous example, the weighted product of alpha T, and you can show that this weighted product is given by this form. That is 2 alpha minus the square alpha minus T and minus 1 alpha. And then we can iterate this. And you iterate this, then this product doesn't vanish. So like in the previous example, we see that this nilpotency class of this space is also infinite. And now consider group which has rank 1 and is torsion free. So somehow we repeat here this construction from n greater 2. So if you have 8 and this is group torsion free, then this group is co-limit of cyclic group. And also now also applying this construction which was before, namely mapping telescope cylinder, we have just a sequence of spheres, and we get Moore space of type A1. No, but other hand, T is Eilenberg phase of type type A1. So, but if A is abelian, then Eilenberg space is H space. So if it's H space, then we see that the nilpotency class of this space T is 1, because that is abelian space. Okay, so we have also another example but also for so the case A1. Now consider, given a prime, consider the electron determined by sequence of spheres, I mean cycles, where P means a map from a battery cycle, segment of the cycle of degree P. And now we attach a cell E2 to the first S1 in T via identity map. Then we obtain a space, Moore space of type ZP infinity 1. Okay, and then we can show that this space is a union of subspaces XM. And this NXM is RP squared ZP, which was used in the first example. Then from this we deduce, but this nilpotency class of this RP2, this generalization of real projective space is infinite. So from this we deduce that nilpotency class of loop space, of this Moore space of type ZP infinity 1 is infinite. Okay, I also have some references, so if somebody would like to go to details, then I will be happy to send this. Okay, and that is the end of my talk. So thank you very much for your kind attention. And now I'm going to stop.
Thank you very much. Thank you, Marek. Questions? Comments?
May I ask?
Sure. Okay, Antonio, this is very nice. Okay, please.
So, what is the relation with this work by Steve Theriot, when he proved that in many cases nilpotency of loop spaces is related with a weak category or weak co-category in the sense of Ghanea? Do you know this work? So,
by who could you repeat the name?
Steve Theriot. Steve Theriot.
Se ve rarísimo.
Do you know him? No.
Okay, I know, but
products, and he proved that in the potency of Lie groups is related in favorable cases with a weak co-category of the space of the classified space.
Yeah, okay, I know this paper, yeah, and then.
Okay, then how that relates with your calculations? Is your nilpotency, well, I mean, your nilpotency and his nilpotency, sense of nilpotency is the same. So I wonder whether your examples give, well, in case they are infinite, of course, they give that the weak co-category is infinite too. But in the case you give examples of finite nilpotency of Moore spaces, whether then that gives you also a finite weak co-category and both.
Okay, so I was concentrated only on Moore spaces, and then I used the only method which I used was definition and some observation from algebra. That is the main term. So this my tools was only this. So I think that, but I don't know if it's easy. Also, maybe your question was if I able to deduce this result from the result which I mentioned. This I don't know.
Well, there is an equation, a kind of an inequation that relates both the nilpotency of the loop space with the co-category and weak co-category of the.
Yeah, but here is something specific. We are looking for loop on suspension, and if you and then this is a specific situation. Of course, this result, could be used in other cases. So, somehow a suspension destroy nilpotent. We are loop, more space is a suspension, and then you're taking loop, and you are in specific situation. And for this situation, and then with a special case of this is more space.
Mm-hmm.
Yeah.
My second question is, do you know there are other definitions for nilpotency, like I don't know, the one that applies also to classifying spaces of groups or in general loop spaces, which is a Biedermann-Dwyer.
Yeah. I know this paper. I don't know the details, but I studied this paper.
So is there any relation with the Biedermann-Dwyer definition of nilpotency and how it relates with your examples? Can you calculate the Biedermann-Dwyer nilpotency?
I cannot answer this. I use some classical definition only. But I think that this result which you mentioned is some generalization of this classical case. I only concentrate on the classical definition by Badgania. And then I think that the result which you mentioned that somehow advanced but I cannot tell you if this could be deduced from that.
Okay, thank you.
Okay, thanks. But thanks for the question.